Man-made nanomachines are tiny devices, often just a few nanometers in size, that can move on their own by converting chemical energy into mechanical motion. They work by harnessing chemical fuels, such as hydrogen peroxide, which react on a catalytic surface to generate forces that propel the nanomachine forward. For instance, when hydrogen peroxide decomposes on a specially coated surface, it produces oxygen bubbles. These bubbles push against the nanomachine, giving it the ability to self-propel in a liquid environment. How does this self-propulsion happen? In these systems, the chemical reaction creates a localized burst of energy that generates a small thrust. The design of the nanomachine is crucial. By carefully structuring the catalyst and fuel flow, engineers can direct the motion in a controlled manner. This means that even at such a minute scale, these devices can navigate through complex fluids, almost like miniature swimmers. Beyond their autonomous movement, these nanomachines can also be guided using external fields. For example, if a nanomachine is built with magnetic components, applying a magnetic field can steer it toward a specific target. Imagine a tiny robot that could be directed with a remote control to deliver drugs to a precise location in the body, or to clean up a pollutant in a contaminated water source. The ability to control these machines externally is a game changer because it adds an extra layer of precision to tasks that require targeted action. Why is this combination of self-propulsion and external control so important? It opens up a wide range of applications. In medicine, such nanomachines could be used for targeted drug delivery, where they carry therapeutic agents directly to disease cells, minimizing side effects and maximizing effectiveness. In environmental science, they might be deployed to seek out and neutralize contaminants in water or soil. In the realm of chemical synthesis, these devices could act as micro-reactors, mixing and processing chemicals at a scale that allows for unprecedented reaction efficiencies. What challenges remain? While promising, these technologies face obstacles such as controlling their movement in complex biological fluids, ensuring they are safe and biocompatible, and scaling up their production for practical use. Despite these challenges, research is progressing rapidly, and each breakthrough brings us closer to a future where nanomachines play an integral role in various fields. In summary, man-made nanomachines that self-propel using chemical fuels and can be controlled by external fields represent a fascinating intersection of chemistry, physics, and engineering. Their ability to convert chemical energy into directed motion and to be steered with precision makes them ideal for applications ranging from targeted drug delivery to environmental remediation and advanced chemical synthesis. As researchers overcome the remaining hurdles, these tiny machines may soon become powerful tools in revolutionizing technology at the smallest scales.
1. Introduction to man-made nanomachines. Scientific explanation. Man-made nanomachines are engineered devices on the nanometer scale capable of performing specific tasks autonomously. They operate in environments where chemical reactions and physical forces behave differently from the macroscopic world. These tiny machines are designed to harness energy from chemical fuels and perform controlled movements. Their development represents a convergence of nanotechnology, chemistry, and physics to create functional devices at the molecular level. Example: researchers have developed nanomachines that can move through liquid environments by converting chemical energy into motion. Analogy: it's like creating miniature robots that can navigate a tiny maze using the energy from a small battery. 2. Autonomous self-propulsion mechanisms. Scientific explanation. Nanomachines achieve self-propulsion by converting chemical energy into kinetic energy through specific reactions. These mechanisms often rely on catalytic processes that decompose chemical fuels and generate localized forces. The propulsion occurs without external mechanical input, allowing the devices to move autonomously in a fluid medium. This self-propulsion is fundamental for applications where directed movement at the nanoscale is required. Example: some nanomachines use catalytic reactions on their surfaces to generate thrust, enabling them to move in a controlled direction. Analogy: it's like a miniature jet engine that propels a tiny vehicle forward using a small burst of fuel. 3. Chemical fuels for nanomachine operation. Scientific explanation. Chemical fuels, such as hydrogen peroxide or other reactive compounds, provide the necessary energy for nanomachine movement. The fuel undergoes catalytic reactions on the surface of the nanomachine, releasing energy that is converted into motion. The choice and concentration of fuel determine the speed and efficiency of the propulsion. This fuel-driven mechanism is crucial for powering nanomachines in various applications. Example: a nanomachine may use hydrogen peroxide as a fuel, where its decomposition generates oxygen bubbles that push the device forward. Analogy: it's like using a tiny combustion engine where a small amount of fuel produces enough energy to move the machine, similar to how a remote-controlled car operates on a battery. External fields such as magnetic, electric, or light fields can be used to steer and control nanomachine movements. By applying these fields, researchers can influence the direction, speed, and behavior of nanomachines in real time. The interaction between the external field and the nanomachine's properties allows for precise manipulation, overcoming the randomness of molecular motion. This controlled guidance is essential for targeted applications in complex environments. Magnetic nanomachines can be directed along predetermined paths by applying a magnetic field, enabling them to reach specific targets. It's like using a remote control to steer a toy car. The external signal guides its movement with precision. In medicine, nanomachines hold the promise of targeted drug delivery, diagnostics, and minimally invasive surgeries. Their small size allows them to navigate through bodily fluids and tissues, delivering therapeutic agents precisely where needed. Controlled movement via external fields ensures that they reach specific sites, such as tumors or areas of infection. These applications aim to increase treatment efficacy while reducing side effects and invasiveness. Nanomachines could be engineered to deliver chemotherapy drugs directly to cancer cells, minimizing damage to healthy tissues. It's like sending a precise, miniaturized delivery drone directly to a specific address, ensuring that the package reaches the intended recipient without detours. Beyond medicine, nanomachines are being explored for environmental remediation and industrial chemical synthesis. They can be designed to selectively interact with pollutants, catalyze chemical reactions, or assist in the efficient production of chemicals. Their autonomous movement and precise control enable them to operate in complex, dynamic environments. These capabilities make nanomachines valuable tools for cleaning up contaminants or enhancing industrial processes. Nanomachines might be used to break down toxic compounds in water, accelerating the purification process in contaminated environments. It's like using tiny cleaning robots that can navigate through a messy room to pick up and dispose of specific items, leaving the area spotless. The fabrication of nanomachines involves advanced techniques such as chemical synthesis, self-assembly, and lithography. These methods allow for the precise control of size, shape, and surface properties, which are critical for their functionality. Innovations in fabrication have led to more robust and efficient nanomachines that can operate reliably in various conditions. Continuous advancements in this field are paving the way for more complex and capable nanoscale devices. Laboratory processes now enable the production of nanomachines with intricate designs that allow for controlled movement and interaction with their environment. It's like building intricate models from tiny Lego pieces. The precision in design and assembly results in a functional, miniature masterpiece. One of the main challenges in nanomachine research is ensuring their stability and functionality when transitioning from laboratory conditions to real-world applications. Factors such as fuel depletion, external interference, and material degradation can affect their performance over time. Researchers are working on improving the durability and scalability of these devices to ensure consistent performance. Addressing these challenges is crucial for practical applications in medicine, industry, and environmental science. In experiments, nanomachines may perform well initially, but lose efficiency over prolonged periods, prompting improvements in design and materials. It's like a high-performance sports car that needs regular maintenance and fine-tuning to continue running at peak efficiency. Robust engineering is essential for long-term performance. Future research on nanomachines will focus on integrating more sophisticated control systems, such as those using artificial intelligence and advanced sensor technologies. These improvements aim to enhance the precision, adaptability, and multifunctionality of nanomachines. Interdisciplinary collaboration among chemists, engineers, biologists, and computer scientists is crucial for driving innovations in this field. The ongoing developments promise to unlock new applications and transform industries by harnessing the unique properties of nanoscale devices. Emerging projects envision nanomachines that can autonomously adjust their behavior in response to environmental cues, leading to breakthroughs in smart drug delivery systems. It's like upgrading from a simple remote-controlled toy to a smart device that learns and adapts its behavior over time, offering increased functionality and efficiency.